All right. So, guys, let's move on to the next part of the lesson. So, we'll now discuss how to find the center of mass of a uniform semicircular lamina. So, when it comes to lamina, okay, when it comes to the circular arc, basically you have already learned the equation in M2. Okay, but now what we are going to do is we are actually going to prove the equation. Okay, so we will first specifically do the calculus proof for a semicircular lamina. All right, so this is a special case. So we will learn how to do this, and also we will do the proof for a lamina with a different angle. Now over here, a semicircular lamina means you have 180-degree here, right? Okay, so first of all, we'll see how to find and how to do the proof. Okay, so you must be familiar and you must be able to derive this proof. If they ask in the exam, you should be able to write down the complete proof for the center of mass of a semicircular lamina. Okay, so now how do we do this proof? So the theory that we are going to use is exactly kind of the same thing that we used in the previous section. So in the previous part, if you noticed, I hope you saw that in the previous part, the area that we were finding, when we use calculus, you saw that we divided the whole area into strips, right? So because there is a lamina. So basically the lamina is all the time it's constructed under a curve. So what we do is, because we divide this into small strips, uniformly small, so tiny strips, so that it becomes a rectangle. Right, so this is what we did in the previous case. So in the previous case, you saw that the area, the strips were formed by the curve. The strips that were formed were bounded by the curve and the x-axis, right? So over here also we do the exact same thing. So we are going to divide this semicircular lamina into strips. Okay, so that's the method of calculus. So small so that each strip actually becomes a rectangle. Okay, so the strips are so small that it actually becomes a rectangle because it's so tiny. All right, so we'll divide this into strips, but now you can see your strip doesn't stop at the x-axis. Can you see? The previous one stopped over here, right? Did you notice, like, the previous strips were like this, right? This is how we divided strips in the previous case. But now, since it's a semicircular lamina, you have the area going to the other side as well, right? So your strips should come all the way down. Do you notice that? So I'm just drawing a little bit of a large strip to make you see it, but these strips are so tiny. Okay, so you divide into millions of strips. That's what's happening here, like so tiny. Okay, so the strips are like really, really small. Okay, so that's what's happening, and each strip is there having a width of delta x. So I am drawing one in a noticeable size so that we can mark all the information, but this is really small. Okay, so it's really and almost in delta x is going to be really, really small. Okay, so now let's name the strip here. So we'll take a particular strip as PQRS, and then, so guys, you know what we do here, right? So for each strip, you're supposed to write the mass and you're supposed to write the center of mass, right? You're supposed to write the mass and the center of mass of each strip. So let's take the individual strip PQRS. Okay, so first I want to write the mass of PQRS. So mass, in this particular lesson, how do we take the mass? When it comes to a lamina, mass is proportional to the area. Okay, mass is proportional to the area. That's the whole theory, right? And you know that this is, we take the strips so small so that this actually becomes a rectangle. So this PQRS is a rectangle now. So guys, over here, let's take the coordinates. So I'll take the coordinate. Now, PQRS is a general strip, right? It can represent any strip on this particular lamina. So this point. So I'll take this point as point X, okay? X is a general point. And so basically at the point P, okay, at point P, the coordinate will be the X coordinate is X and Y coordinate, I'll just say it as Y, okay, which means this height is Y. Is that okay? So at P, at the point P, the X coordinate is generally, I'm taking it as X, and the Y coordinate, I'm taking it as Y. Okay, so now let's take the mass. Okay, so mass is over here the area of the rectangle, length into breadth. So can you all find the area of the rectangle in terms of X and Y? All right, guys. So how do we get the area? Now the thing is, you're taking the area of the entire strip, right? And you know that if this now we got this particular length as y, right? So if this length is y, guys, what about the other side then? So you know it's a semicircle, and definitely this is a line of symmetry. The x-axis is drawn as a line of symmetry here, right? So whatever the length you have here y, the other side also has the exact same length y, right? So which means the full length of this particular rectangle is 2y. Great. So the full length of this rectangle is 2y. And what about the width? So the width, I think you can see I have clearly marked it. It's delta x. The width is delta x. So 2y into delta x. So this is the area actually. So to make it mass, you have to multiply it by rho. So rho is the mass per unit area. Okay, so the area should be multiplied by rho to make it mass per unit area. All right, guys. So this is going to be 2y rho delta x. All right, guys. So this is the mass. Also, let's get the center of mass of the strip. I want the center of mass of PQRS strip. So guys, by the way, when we were doing M2, okay, so when we were doing M2 center of mass, there was a very special rule. So whenever we were dealing, when we were trying to find the center of mass, do you recall one thing to always check? One thing to always check is in your shape, always find if there is a line of symmetry. Because if there is a line of symmetry, always your center of mass will lie on that line of symmetry. Now in this particular shape, the semicircular lamina, you can see it's lying, I mean the x-axis is the line of symmetry, which means what? Which means if this x-axis is the line of symmetry, the center of mass of this semicircular lamina is definitely somewhere on this line of symmetry. So which means one coordinate is already there. One coordinate is already found. What's the coordinate you know here? All right. So when you have a line of symmetry, definitely one coordinate is already there from x bar and y bar. So over here, if you check, since the line of symmetry is there, let's say, so if this is the G, so over here you can see in the center of mass, the x bar distance, we don't know it yet, but the y bar is surely 0 because you are on the x-axis. So y bar is actually in the sense the final answer y bar is 0. So you don't really have to find y bar here. The only thing you need to find here is the x bar. All right. So anyway, that's for the final answer. Okay. Now let's take the center of mass of this particular rectangle. Okay. Let's come back to our strip. Okay. So let's come back to our strip. So coming back to our strip, where do you think the center of mass is going to be? So it's a rectangular strip, and you know in a rectangle, the center of mass is going to be exactly in the middle of the rectangle, isn't it? The center of mass of a rectangle is exactly in the middle of it. So can you all get me the coordinate of the center of this particular rectangle? What is the coordinate of the center of this particular rectangle? All right, guys. So when it comes to the center of mass, okay, so you can see the center of mass of the rectangular strip. Let me erase this G. This G represents the center of mass of the whole thing. Okay, so we are first concerned. Now we'll be concerned only about of this rectangular strip. So basically, the center of mass of the strip should be in the middle, right? It should be in the middle of that particular rectangle. So what's going to happen here? So basically, you can see that this is exactly in the middle of this delta x strip, right? So don't the x coordinate is not simply delta x over 2, okay? Because I can feel that some of you might just say half of delta x. No, it's you can see you already have this length x because x already covers this particular length, right? So it's x plus the half of delta x, right? Because you have to give when you're giving a center of mass a coordinate, coordinates are measured from the origin. So you have to give the coordinate distance from the origin, not just the half of delta x, but x plus half of delta x to give the full distance from the origin, right? And y coordinate, of course, you can clearly see it's 0 because you are on the x-axis. So y coordinate is 0. And guys, if you recall, I told this to you in the previous proof as well. So delta x, now you know that we are getting these strips like so small, right? The strips need to be really, really small in order to make this as a rectangle. So these strips are so tiny, and delta x is actually a very small change in x. And you divide that by 2, right? So delta x is a really small change in x. You divide that by 2 and you add to it. So do you recall what I told you in the previous section? So if you recall in the previous section, I told you delta x is really, really small. Divide that by 2, it gets even smaller. And when you add it to x is quite a big digit here, right? So x might be a large figure. Okay, so when you add something really, really small, okay, into a figure, so maybe you say x is something like to do with, I'm just randomly giving a figure here. So if x is 2 and, delta x is a very small change in x. So maybe 0.5 zeros or 10 zeros, right? Delta x might be that small and you divide by that by 2 and it's even smaller. So you'll have something like, with so many zeros, okay? So, and then when you add it to 2, you can see it's actually negligible because it's so small here. Okay, when you add these two guys, it's so negligible. So it's actually x comma 0. So this is the theory. This is how you always write the center of mass. Okay, so we discussed this in the previous part as well. Okay, so this is the center of mass of PQRS. That's done. All right, guys. Okay, so what's the equation for the center of mass? We are going to use the center of mass equation from the M2 equation, right? So what was that? Sigma mi xi. I'm going to find the x bar first. Sigma mi xi equals total mass into x bar. Capital M into x bar. Total mass means, okay, so basically sigma mi. Sigma mi means the total mass. All right, guys. Sigma mi xi equals total mass. I'll put it as capital M into x bar. Guys, over here, now in the previous section, you saw I even found sigma mi separately. If you recall, in the previous section, do you recall I found sigma mi also separately? Okay, because sigma mi had to be found separately, right? Over here, can you see we found sigma mi by taking the sum of all the masses only. We took the sum of all the masses alone on its own. Okay, but over here, this is actually a special case. A special case in the sense we know the actual shape. The actual shape is it's a semicircle. So when it comes to the total mass, guys, total mass is, in other words, is the total area, right? Total area multiplied by rho. Do you agree? Total mass means it's actually total area times rho, right? Because rho is the mass per unit area. So in the previous section, we had a kind of like, it was not a proper, I mean, we did not know the proper shape, right? So we had to integrate to get the area. But now the full area is actually a semicircle, isn't it? So total area is the area of a semicircle. If you want, you can do the integration. I mean, you can do it on its own and get it, but it would save you a lot of time. It will save you a lot of precious time if you get the total mass by taking the total area, and since the total area is the area of a semicircle, it will save you a lot of time. So what you need to do here is directly, instead of going for the integration method, now total area is half of pi r square, isn't it? Because its radius is r, so half of pi r square into rho, saving you a lot of time. All right, guys, so total mass is there. Okay, so let's apply now all these values into the equation. All right, so guys, let's actually apply the values now. Okay, so sigma mi is the total mass. Okay, so I use capital M for that. So this total mass is the capital M here, okay, to make things easier. All right, so sigma, so basically over here, we multiply the mass of every individual rectangle is multiplied with its own center of mass. So fortunately here, we have found the mass and the center of mass of a general rectangle, because PQRS is written in terms of X and Y. It could represent any one of the strips in this particular, because, there are many millions of strips here, right? So there are many. So this represents any one of them, right? Because we have marked everything in a general form. So what's the mass? So what's the mass? Mass is 2y rho times delta x, right? So mass is 2y rho times delta x, and center of mass, x coordinate is x. Can you see? So you multiply the mass with the center of mass. I'm going for the x coordinate. So multiply with x. And guys, what about the limits? Now over here, the summation, from where to where do we add the strips? So you can see your strips start at x equals 0. Can you see? The strip start at x equals 0 and it ends at x equals r. Can you see? You start from 0 and you end at x equal r. Okay. So this is so when you take the summation, it means you add all the you add all those rectangles, because you don't have just one rectangle here, you have many. So we add all the rectangles between 0 and r. Okay, and then total mass is half pi r square rho into x bar. All right, guys. So you just need to make x bar the subject here. First, let's apply the equation. So you know, as delta x, now you know, to make this strips as better as possible, to make this as accurate as possible, the rectangle, y'all, delta x must be what? The delta x needs to be as small as possible, right? Okay, so delta x needs to be as small as possible. So as delta x closes to 0, the summation becomes integral. Okay, as delta x closes to 0, the summation becomes integrals, and you have over here integration from 0 to r 2y rho, and put the x inside. Delta x is what becomes your dx. Okay, delta x becomes dx. Over here on the other side, we don't have any issue. Half pi r square rho x bar. Is that okay, guys? Okay, so now we'll work on the, we have to work on the integration here. So over here, the 2 and rho, you can bring it out of the integral sign. Integration 0 to r, and you have here 2 and rho comes out. So y and x, so xy remains inside the integral. Xy are anyway not constants, right? Xy are variables. All right, guys. So now we have an integration in our hands. We need to integrate xy with respect to x. All right, guys. Okay. So now how do we perform the integration? And most importantly, our integration is happening with respect to y. What do we use for y now? Okay. So because we need to use a we need to write y in terms of x. So how do we get the equation? Basically, y represents the equation of our curve here, isn't it? Y represents the equation of the curve. Okay, so the y represents the equation of this curve. So if you recall, to get the equation of the curve, you can see it's actually y represents over here a part of a circle, right? Even though you don't have the full circle, y, the curve over here still represents a part of a circle. So basically, you can use over here, what's the equation of a circle? So you have learned x minus a square plus y minus b square equal r square. Do you recall this from P2? This is the equation of a circle with center a comma b and radius r. This is the equation of a circle, center AB, radius r. So over here, I have a circle with center 0, 0 and radius r, which means it's going to be x minus 0 square, which is x square, and then y minus 0 square, which is y square equals to radius square. Can you guys see? So basically, this part of the curve, part of the curve has the equation x square plus y square equal r using the P2 formula. Center is 0, 0. All right, guys. So from here, I can make y the subject. I get here y square equal r square minus x square. And that gives me y equals root r square minus x square. All right, guys. So we'll work with this now. All right, guys. So it's time to substitute. So x times what's y? We just found y is root r square minus x square with respect to x. Okay, so we don't have any problem in the other side. The other side is already done. Okay, so this side we don't have any integration now because total mass is known. Okay. All right, guys. So now we have a hurdle here. What's it? You need to perform an integration, right? You need to perform an integration of x times root r square minus x square. So guys, to do this integration, you need to remember the P3 integration formulas. Okay, so this is the integration that you learn specifically in P3. All right, guys. So what's the rule? All right, guys. So in order to perform this integration, as I told you, you need to remember the P3 rule. So this is the P3 rule that we are specifically talking about, the reverse chain rule, right? So f dash x fx to the power n, the answer is fx to the power n plus 1 divided by n plus 1. Okay, so I've actually kind of like, just given a few examples to remind you of that anyway. So you need to remind this in P3, right? Okay, so let's directly apply. So basically, you can see here, this is 2 rho times Integration 0 to r. This is x times r square minus x square root means it's a power half. All right, guys. Okay, so basically you can see now if you apply this rule, your fx, as you can see, this is the fx part. Can you see n is the power half? Okay, and then what's the differentiation? So basically you need to have the differentiation of this inside on the outside. So what's the differentiation of r square minus x square? R square minus x square, r is a constant, that's 0. X squared minus x square here, guys. Be cautious, this is not just x square, but a minus x square. So minus x square differentiation is minus 2x, right? It's minus 2x. So guys, over here you can see we have a crucial component. The x is there, but we are missing. In order to create our perfect f dash x, we are missing a minus 2. So you have to input a minus 2 and then to cancel the effect, put a minus 2 out as a division. Can you see? So minus 2 in here and a minus 2 out. All right, guys, because we need the minus 2 in order to create the perfect f dash x. Can you see? So it's happening regardless of the power. Okay, so the inside differentiation must be perfectly there outside over here. So you can see minus x square differentiation is minus 2x. But the x was there, minus 2 is missing. So we input minus 2 and to cancel out the effect, we input another minus 2 outside in the denominator. So it does not make any difference to our sum. All right, guys. So now let's perform the integration. So here minus 2 minus can cancel. Basically, you have a minus rho times. Let's perform the integration now. Okay, so I'll use a bracket here. So what's happening here? Fx to the power n plus 1. Yeah, fx is r square minus x square to the power n plus 1. Yeah, n is half. Half plus 1 is 3 over 2. Divide by 3 over 2. All right, guys. So close the bracket. So this is, we are done with the integration now, but you need to go with what? The integration limits are from 0 to r. You have to go with the integration limit. Okay. So the other side, you can just let it be there. Okay, so we let it be there. Okay, so let's simplify. So minus rho times, you guys can see this is the denominator 3 over 2. When you take it to the correct side, it's 2 over 3, right? 2 over 3. So over here, let's input the limit r square minus x is, we replace x with r. Can you see? So minus, in the middle, minus sign, again 2 over 3 times. R square minus x is now replaced by 0. Can you guys see? So I just replace the x with the limit because we had to replace our x with the two limits, right? So minus rho times 2 over 3 r square minus r square is 0. So basically the first part of this is 0 minus 2 over 3 r square to the power 3 over 2. So r square power 3 over 2, the square and the half cancels, then you get r to the power 3. The powers multiply, right? 2 and 3 over 2, the powers multiply. So you get r cube. Half pi r square rho x bar, and over here minus minus becomes plus 2 over 3 rho r cube equals half pi r square rho x bar. So guys, over here now we can cancel a few terms. For example, the rho can cancel out, right? I'm supposed to make x bar the subject. Okay, so we'll make x bar the subject. Over here I get 2 over 3 r cube times, let's bring the terms to the other side, the half, the 2 here comes up as a multiplication, the pi and the r square comes down, right, equals x bar. So you can cancel a few terms. You can see, you can multiply. So 2 times 2 is 4. R cube and r square cancels. 1 r remains at the top, and at the bottom you have 3 pi. 4r over 3 pi is equal to x bar. Yeah, guys, so this is it. So this is the center of mass of a semicircular lamina. And this is the calculus proof of it. So I have done the calculus proof for the center of mass of a semicircular lamina. If they ask you to do the proof, you must be able to completely do this proof. Okay, and if they want you to directly use the result, you can use the result. Sometimes they'll give you the result, the center of mass of a semicircular lamina is 4r over 3 pi, and they'll ask you to continue from there. Then it's a different story. But if they ask you to do the proof, the calculus proof, this is the full proof. Okay, over here, once again, I need to emphasize because I think some of you might be wondering, were asking me, over on this side. Now, in the previous case, we had two integrations, right? Did you notice that we had integration over on both the sides? Okay, so in this case, I only had one integration. So what's the reason for that? The reason for that is the total mass. In the previous case, the total mass was an unknown area. The total mass was an unknown. I mean, this is not a shape that we know the area of. So then we have to go with the total mass by taking sigma mi. But over here, in this case, the total mass sigma mi, okay, the total mass, this is the mass of a strip. So total mass is the sigma mi of that. But the thing is, I don't need to apply that equation here for sigma mi, because when it comes to the total mass is proportional to the total area, and the total area is the area of a semicircle. So semicircle, area of a circle is pi r square, area of a semicircle is half of pi r square. All right, guys. So that's the reason why we don't need to go for another integration. So of course, if you go with this, you can also go with this. That's perfectly fine. You can use 2y rho delta x summation and use that and actually go for the integration. So you will get the area of the semicircle half of pi r square into rho. Okay, so you'll get this. Okay, so this is, I hope you guys understood. So if the total mass is a shape that you actually know, it's better to immediately use that so that the work is reduced. Okay, so basically this is the rule. This is the center of mass of a semicircular lamina. All right, so guys, when it comes to the application of this, actually, the application is really simple, right? The proof is the hard part. Actually, we don't, there's not much of a sum that we are required to do it, to be honest. Why? Because if they give you the radius, so say for example, the radius is 5 units. So if the radius is 5 units, for example, okay. So in the question, if they say if radius is 5, all you had, or 5 centimeter, all you had to do is to input radius as 5. That's it. And you get the center of mass. Simple as this. So this is the center of mass. You don't have much to do here. Not yet anyway. So we will come for composite figures later. At this point, let's first finish off the theories. Okay, all these different types of types and formulas that you need to know. So basically, if you have a semicircular lamina, the center of mass is 4r over 3 pi along the axis of symmetry. Okay, so along the axis of symmetry, you have a distance of 4r over 3 pi. And if you know the radius, substitute the radius and you can get the center of mass. Okay, and if they ask you to do the proof of it using calculus, you must be able to write down the proof. Okay, so there's not much, nothing, there are no extra sums to be done here. So we'll just go with this and we'll now move on to the next part. Okay.